Okay, so today we're going to talk about some different properties of sampling distributions. Firstly, you're going to see sampling distributions. We're talking about the sample mean. That is written as x bar. We've learned before. One thing that is true, and this is rule number one, is that the actual mean of our population, okay, is going to be the same as the mean of our entire sampling distribution. Now, that doesn't mean that we're always going to get our sample mean to equal the true mean. It's that if we were to find the distribution of all possible samples of a certain size, we average those and we found the mean of that distribution, it would be the same as the mean of the main population. And that's really important for us. The second rule says that the standard deviation of our sampling distribution is going to be our population standard deviation divided by the square root of the sample size that we used to for our samples. So, for example, if we had a sample size, if n was 4, we would take our normal standard deviation and we would divide that by the square root of 4, which would be 2. So the standard deviation in that case of our sampling distribution would be half that of the normal. And we can, obviously, any type of square we can take in. So if our sample size was 9, it would be 1/3 that of normal because the square root of 9 is 3. And so on and so forth. And you can see that, if we took a sample size of 100, very large sample size, then the sampling distribution would have a standard deviation 10 times smaller than that of the original. And that's because as we add terms to our sample, we keep increasing the size of our sample, we're going to add more and more terms that are going to balance each other and create a closer value to the mean than would, isolated smaller samples. Rule 3 says when the population distribution is normal, the sampling distribution of x bar is also normal for any size. So if we know that our population distribution, this is everyone, if we know that that is normal, then our sampling distribution is also going to be normal. We know that that's going to be true, and it depends. The size will depend on, and the shape will depend on our sample size, but it's going to be symmetric. Now, Rule 4 says that if n is large enough, it does not matter what the population distribution is. It doesn't have to be normal, but if we take a large enough sample, then it will take care of it and it will become normal as well. And that magic number is going to be 30. So Rule 4 says that, if n is 30, our sampling distribution is normal. Will be normal. And this is regardless of what the population distribution is. So this is a magic number. So if n is 30, regardless of our population distribution, we will have a normal or well approximated distribution that could be normal for our sample. Now, this kind of shows that same thing that I was talking about. Here, this wide population, that's our population. As we increase our sample size, our center is the same. Notice that our center is the same for all three of these. And that makes complete sense because that's what we're going to see. These are all samples of a size 4, all samples of a size 16, and so on. And what you're going to see is that as we go up to a sample size of 4, we have half the standard deviation of before. So we're going to have half the variation. As we go up to a sample size of 16, we will have 1/4 of the variation of the normal. And now, even if we have a skewed distribution at first, the more and more that we add to our sample size, the closer and closer it's going to become a normal distribution. And our magic number, again, is going to be 30. So even here, with a skewed distribution that looks like this, the closer and closer that we get to a a large sample, so the closer and closer we get to a sample size of 30, the more and more normally approximated our sampling distribution is going to be. And all the old rules that we use to find z-scores we used to find, were going to be our observation minus our mean over the standard deviation. Well, all we have to do in order to take this for a sampling distribution is update our data. That's it. So what we can do is if we wanted to say this for a sampling distribution, so we would say, okay, well, instead of x and observation, it's going to be our sample mean, because that our sample is kind of our observation now. So we're taking the sample mean. Well, we would then subtract away the mean of our sample standard deviation, or our sampling distribution, which is the mean of x bar, and then we would also have our standard deviation of that. So this all works together. But we don't need to know all of these things in order to find it. We know from earlier, from Rule 1, that this equals our regular mean. So we can actually replace that with our regular mean. So nothing changes there. We also learned earlier that the standard deviation of our sampling distribution is our population standard deviation divided by the square root of n. So we can replace those. So really what we need to know is what was the observation we had from our sampling mean. So what is our sampling mean, and what was the sample size? If we know that, then we can effectively find any z-score that we're looking for. And again, as I've stated many times, we can apply the central limit theorem, which means that we can basically approximate, we can use the normal distribution to find stuff, regardless of the shape of the population distribution, if our sample size is greater than or equal to 30.